So, when we are talking about the mass spectrometry, we need to start with the periodic table of elements. And there's a reason for that is that if we see the table, we will see some numbers here. For example, carbon. Carbon here, you see this kind of atomic number for carbon shown here is 12.0107. And actually why I'm showing this periodic table of elements is that actually you cannot use those numbers at all in mass spectrometry. And the reason for that is that these numbers you see here are average values. They are weak average values of natural isotopes of carbon, for example, here. And weak average means that it takes into account the different types of isotopes there are and their quantities. So in case of carbon, we have in nature both carbon-12 isotope and carbon-13 isotope. But there's much more carbon-12 isotope, and that's why the weak average of the carbon here shown in the table is a bit only slightly more than 12. But in the mass spectrometry, we don't use any average values. We use the true values, and we monitor true values of masses. Usually the ones found in molecules, and of course in the molecules we have lots of these atoms. And so for the carbon 12 isotope, somebody has decided that the atomic the mass value for that isotope is exactly 12.0000, and all the other isotopes, all the other atoms are compared to that. And that means that also none of the other atoms or other isotopes have this kind of exact value with the decimals, zero decimals everywhere. So they are all the others are compared to the carbon-12, and these are called monoisotopic masses, meaning that they are the true values of the masses of the isotopes. And these are also the values that we can read and see in our mass spectrometric results. So you need to forget the periodic table of elements in sense that you cannot use these numbers in any of your calculations to do with your mass spectrometric results. So what is mass spectrometry, first of all? It's mass spectrometry, meaning that you can measure masses and masses of molecules. Of course, we might be interested to see sometimes if you want to verify some structures, identify structures, we are not sure what we are measuring. Like if we are getting peaks from the chromatography, we might not be sure what each peak represents. Sometimes we have standard compounds that can be used to verify, but sometimes we don't have standard compounds or reference compounds. And sometimes even if we do have, we are still a bit uncertain on the identities of the chromatographic peaks. So here the mass spectrometric detection might come to help us to verify these identifications because we really can measure the mass value of that molecule, the weight of the molecule. And so this can be used in the identification. It can be used for quantitative analysis as also. At the same time, if we have a big response, large intensity in our mass spectra, we can compare those responses to each other. The peak areas, for example, I was explaining in the chromatograms, we can also calculate these kind of peak areas from the mass spectrometric data to get the quantitative analysis. But that is based on these molecular weights, of course, because those are measured with mass spectrometry. We can use mass spectrometry to analyze complicated mixtures with some instruments that are very accurate and have a high resolution, high resolving power. They can also be used to determine elementary composition of some components, some molecules. If we don't know what they are. And so we have different types of instruments, also different types of needs. And so depending on what the needs are, we need to consider what is the right choice of this mass spectrometric analysis that we will choose. Of course, it's also a matter of money, how much is available, because some of these instruments are very, very expensive. Okay, so maybe we can let's take a look at here. I have in my material here, I have a lot of text which you can read at home. I'm not going to all of that in detail, but let's start maybe. I will show you a picture, or draw a picture here. So you remember last time you saw these chromatograms where the x-axis was time and y-axis was intensity here. So time and intensity. And we had all those chromatographic peaks there as a function of time. We had got these peaks. Sorry, these are not looking that nice because I'm doing this freehand. So these peaks here. And time axis, intensity axis. So this in chromatography, the intensity or the response here is depending on the detector. And the detector can also be a mass spectrometer. But what is now unique for the mass spectrometer is that in addition to these chromatograms, we can also get the so-called mass spectra. Let's draw a mass spectrum here. So now if we have this x-axis here, it's not time, but rather it's m divided by c. And what's that? It's mass divided by charge. And now what this means, okay, here y-axis is still, it's the intensity or the response, detector response that we get. Okay, so we have, if we are using chromatography, as we quite often are, we use chromatography to introduce the samples to mass spectrometer. So, for example, if we are using liquid chromatography and we have this chromatographic peak here, and the information that we get from the mass spectrum is actually, it could be what's inside this peak. So we drag across this peak with our computer software. We drag across this peak, and what happens? Our software opens as this mass spectrum, and what appears here are some peaks. So in this mass spectrum, then we will see these different components with different mass values or MZ values that are eluting out of the column into the detector. So those components that are within this chromatographic peak. So this is the chromatogram, which you can also, if we are utilizing chromatography in mass spectrometry, we can also get these chromatograms and see them. And then here we have mass spectrum. So mass divided by charge. And if you think about the small molecules and their ionization, so first of all, why we have charge here? The reason is that with mass spectrometry, we can never detect neutral molecules. We always need to have ions. And so we need to make ionization. We need to ionize our components, which are typically molecules. And then when they are ionized, they can be singly charged, or they might have more than one charges, and so that will increase the Z. But in case we have these rather small molecules, typically the Z is 1, which means that with the small molecules, when the Z is 1, the mass spectrum really represents the mass of the molecule. But in case we have larger molecules in our samples, then they appear with more than one charge state. Then the Z could be 2, 3, 4, even more than that. So that needs to be taken into account. So with the larger molecules, what you see here is not only the mass, but it's mass divided by, let's say, 3. And then, of course, it would give a slower value. So this is a mass spectrum. This is a chromatogram with very ugly peaks here, as you see. But now, what makes things complicated is that you remember we were talking about the chromatograms. In chromatograms, we want to see narrow peaks, because if our peaks are narrow, then we can separate neighboring peaks more easily from each other. It gives us more resolution, higher resolution for our chromatographic separation. And depending on our system, these peaks can be narrow or they can be wide. And it's then affecting the chromatographic resolution. But actually also with this mass spectra, when we are measuring these different masses, we also come to face the issue about resolution, which is a separate things of the chromatographic resolution. And the reason for this is that even though the mass spectrum, usually very often we draw it like this, but actually, truly, the mass spectrum it isn't like this. So the true mass spectrum, if you think about the physically or chemically, whatever, even if we draw it like this, quite often showing only the peaks, but actually this mass spectrum is can be like this. Sorry, they don't look nice, but maybe you get the idea. So they are also more or less like Gaussian curves. So we sometimes draw these mass spectrum like these sticks, just to illustrate from illustrative purposes. But these we also, in this case, even we have the x-axis is not time, it's the MZ ratio. But sometimes these peaks can be narrow, sometimes they are wide. And that's called the mass resolution. So with certain instruments, these peaks are narrow. Peaks of mass spectra are narrow. And that also then means that you can separate peaks from each other, even that are very close to each other. And that also means that the differences in the masses of those peaks can be very small if this mass resolution is good and the peaks are narrow. So let's see this a bit. I have an example of that here in the material. Let's go, actually we come back to this picture soon. But I will jump now just slightly here. This example here, for example, if we have, these are now mass spectral peaks, remember, so these are not chromatograms. Here in the x-axis, we have this M-Z ratio. If we have very high resolution in our instrument, it means that the peaks are narrow and actually the differences in between neighboring peaks can be very small. These are all within the range of mass unit 249 Daltons or mass units. And the differences are only in matter of first or second decimal places here. This situation here is so-called high resolution. We gain high resolution mass spectrometers. We can get this information up to the many decimal places, and we can separate different compounds from each other that are almost like each other. Chemically, these three compounds might be very different, but their masses are very close to each other. And in case we have a very low resolution or low resolution instruments, then in non-optimal situation, we could have only one peak in mass spectrum, but actually within the same peak, then there can be three different types of structures, three different types of molecules. Because the low resolution instruments cannot tell the differences within where we have the differences only in these decimal places. They all are kind of more or less 249, but they're different. So if we have complicated mixtures of different types of components that might be having almost the same masses or weights, then we may better have choose high resolution instruments. We don't always need them, because quite often we are analyzing like polyphenolic compounds, and we might not be in a situation where we would be analyzing totally different types of structures. And it might be sufficient to have this situation where we have lower resolution. It might be just enough. Let's go back here for some time now. Let's check now. I was talking about the ionization. So we need to ionize in order to analyze the molecular weights. We need to first ionize the molecules or atoms sometimes, typically molecules. And first, before the ionization, which is shown here, we also need to introduce the sample into the mass spectrometer. And as I said in my examples also, very often the first step is the chromatographic step. So we chromatographically separate different components, and then after that analyze them with the mass spectrometer. Okay, it can be liquid chromatography, LC, gas chromatography, some other two means of introduction, capillary electrophoresis. Sometimes we even introduce the sample directly to the mass spectrometry without any type of chromatography or pre-separation. Because anyway, our mass spectrometer can show us different masses. Even if we have one sample, it might be able to separate all of them based on their different masses or M to Z ratios. We have different ways of ionization. I will introduce a couple of them soon. And what happens then after the ionization is the real analysis. So this is the analyzer part of the instrument. And we have different techniques. So this part is then what really does the important work of analyzing what we have in there. And then after that analyzer is still the detection process, which is based on the electron multiplier or photon multiplier or microchannel plates. It's of course, it's the multiplied signal. The idea is that we get a signal to such a form that it can be detected and also shown in our computer screen. Of course, then nowadays, almost always, we analyze our data with computers, and also most of the work is done there and with this person working and going through the data, of course. So there needs to be somebody trying to make sense out of the results as well, of course. Okay, so the situation actually is, this is just this in this text you can read that these are the average masses I showed in the periodic table of elements cannot be used. It's based on the average masses, and the signal we get with the mass spectrometry, it's not the average signal in that sense. We are interested in the exact or monoisotopic masses, which is the mass of the isotope itself, not any average of different isotopes. And yes, and now let's come still back a bit to this matter of resolution. So this is mass spectrum. This is part of the mass spectrum. And what you see here is a molecule, signal of this molecular ion here. And in this case, it's a negative ion, M minus H minus, which this means that it's deprotonated molecule with a negative charge. And then now you might ask why it's only one compound molecular ion there, but you see 1, 2, 3 peaks here. Why? The reason actually is that the first biggest peak here represents the form of the molecule that only has the carbon-12 isotopes in the molecule. And that's the majority of the molecules. Small molecules usually are such that there's only carbon-12. But naturally, something like 1.1% of all the carbon is actually carbon-13 isotope. So if we are having the molecule of this size, usually there is some of the molecules are carrying one carbon-13 isotope. And that molecule here is shown here. So the mass difference here is only one mass unit, 1 Dalton. So this peak here represents the molecules that have one carbon-13, not only carbon-12, but one carbon-13. Yes. So just a short recap in the chromatogram, we have the chromatographic resolution is good if we have narrow peaks and we can nicely separate neighboring peaks from each other. And this is as a function of time in the chromatogram. And in mass spectrum, we will see the different peaks, different probably either the molecules itself or fragments of the molecules in ionized form. We get the M to C ratio. And if these mass spectral peaks are narrow, like I don't know if these are or not, then if they are narrow, then we can really separate neighboring peaks from each other, even if their mass differences would be very small, as was the case in here, as you see. Not much difference in the masses, but because these peaks are very narrow, you can separate them from each other and really very specifically and then selectively get the information of different types of molecules, even if their differences would be very small. Now, please remember in the chat box is available, and you can always comment or ask questions. And it's very important also that those of you who are not that familiar with mass spectrometry can get used to this and get an ideas. And you probably need to think a bit to really understand some of these concepts to do with these techniques. Okay, so I was talking about the mass resolution. It can be determined with help of two neighboring isotope peaks of one compound, for example, as was the situation here. This is the molecule with only the carbon-12 isotopes. This is the molecule ion with the carbon-12 isotopes, where one of those carbon-12 isotopes is replaced by carbon-13. And that, of course, explains the difference in the molecular weight of one mass unit and one Dalton here. So the mass resolution can be calculated also based on these signals. Yeah, and the instruments that have high mass resolution, they also have potential for high accuracy, of course. But mass calibration is necessary for high accuracy, because even if you have good mass resolution, these values here could be wrong if we have not calibrated our system. That's the same as if you are analytical balances. You need to have really, if you are weighing something with analytical scale, analytical balance, of course you need to know that the zero level is zero level. So the value you get is correct and precise. Same here with these highly sophisticated instruments. To be sure that these values are correct, so we have high accuracy, we need to make this constant calibration, but we against some known components, whose masses we know all the time. So the calibration is important, and if that's made correctly, then all these high mass resolution instruments can also be of high accuracy. But this kind of constant calibration may be needed, and is actually it's necessary. Constant calibration is necessary. Okay, so let's check. I have listed some of the ionization techniques. I just pick a couple of you for closer inspection and introduce them more to you. But there are like electron ionization, chemical ionization are often combined with gas chromatography because they work nicely if we have everything in gas phase to begin with. Then we have this, and these ionization techniques are happening in very low pressure, like in vacuum conditions with the help of vacuum pumps. Atmospheric ionization techniques are then quite often combined with HPLC, liquid chromatography. They can handle the solvent flows, and the ionization takes place after that. Then we have these certain other types of techniques, which I'm not going to introduce to you that much in this lecture, but of course you can study them by yourself and learn more about them. Okay, then we have of course some techniques of historical or marginal value. Most these are old-fashioned, all the better have been made, but then this API, atmospheric pressure photoionization, might have some future potential, maybe, but it still hasn't become that popular compared with these other types of atmospheric ionization techniques like electrospray ionization and atmospheric pressure chemical ionization. So the most common of these ionization techniques are, I would say, the EI with more volatile components and this ESI for less volatile components and often combined with liquid chromatography. And I'm also paying more attention to those ones in these lectures. Then, as you remember, after the ionization, we need to analyze the ions also, and that's happening in these analyzers. And the ones I introduce you more to this afternoon are quadrupoles and time-of-flight instruments. Quadrupole instruments are these so-called low-resolution instrument. As I showed you what is low resolution, low mass resolution, and what is a high mass resolution. But still, they have quadrupole instruments, even though they are low resolution instruments, they can be used in many types of targeted analysis where targeted analysis means we have maybe a more limited type of components in our sample. So it doesn't get so problematic with those with different components that might be having almost the same masses. And also what quadrupole instruments, they are quite cheap. They are quite good in quantitative work. So they are in that they are better than many others actually in the quantitative work. And also if we are just monitoring certain ions present, quadrupoles can be very sensitive as well. But then the time of flight instruments are high resolution. They are consisting of these high resolution analyzers. They are high resolution analyzers themselves. And it means that you can really do this kind of non-targeted work where we have very complicated mixtures and where maybe some of the differences in masses are very small, and you really can take advantage of this high resolving power and high mass resolution, which we can distinguish in between molecules, ions with very small differences in their weights or their masses. Okay, then we have also these ion traps, Fourier transform instruments, orbit trap instruments, and so on. Hybrid instruments are such that combine more than one type of analyzer. Okay, then. So maybe it's good to show you a bit about. Let's go back to this paint. So what we can do is that we can monitor only selected type of masses in our samples. And we just tell the instrument, so to say, that for example, that now I'm only interested to monitoring the molecular ions that have this mass of 239.54. And okay, if it's present, then I will see the peak in the mass spectrum, and it's corresponding to this value there. If it's present in our sample, then we see it. If it's not present, we don't see it. So simple is that. And actually, this is called, when we are only monitoring some selected masses, we can also choose some more, let's say 150.5, and also then we also monitor that, and also might then be seeing signal for that, and that would be interesting to us also. So we are also monitoring that, and if it's present, we will also see peak for it. But nevertheless, when we are only monitoring selected ions like this simply, that's what we call SIM or SIR. Just a moment, I get this back. SIM or SIR. And it means selected single ion monitoring. Actually, I think let's keep only this single ion monitoring here. Or single ion recording. So these are synonymous. So we have a selected single ions that we are monitoring, and if they are present, we see the signal, and if they are not present, we don't see anything. If they are not present, we don't see that. And then the other way of doing our analysis is scanning. And scanning is when we are choosing that we are interested in more than just a couple of different ions. We are actually interested in analyzing a whole spectrum of different masses. So if we have MC, we could choose that in the mass spectrum we want to see all the ions from 100 to, let's say, 1000. Okay, it went to the wrong place. From 100 to 1000. And if in our sample, if we have any of those masses anywhere in between 100 and 1000, then we would see those. Let's say big here, big there, big here, so on. Lots of the peaks. And this is what we call this scanning. And when we are now taking a closer look for first in the quadrupole, I will understand more about what's going on. So this is scan mode. Using the MS in scan mode, we are scanning all the masses from 100 to 1000. SIM or SIR, and this is the scanning, because we want to see everything within this selected mass range. Okay, then we have this concept of tandem mass spectrometry, MS. It's now, if in the earlier example we only have the single MS analysis, be it this SIM or be it this scanned. But we can get better and more selective information if we are utilizing two steps of mass spectrometric analysis in series. And what we usually do, why we are doing this tandem MS, that we might be interested in fragmenting the molecular ion. Why would we be interesting to fragmenting it? It's to get more. We could be more certain that the molecule is what we think that it is. And this good example here is that if we have, let's say that we have this molecular ion that's having this molecular weight, or the MZ value, to be more precise, the MZ value. It could be that we have two different compounds that have the same mass, and we have no way of distinguishing because they are exactly the elementary composition is the same, but they are different compounds. So analyte 1, analyte 2, completely different analytes, but they both are like 239.45. So this kind of simple single mass spectrometric analysis, we cannot tell the difference. We don't know whether it's analyte 1 or analyte 2. But if we do this kind of selective fragmentation of the compound, so then based on the fragments we get, we might be then able to say what compound we have there. Because probably the analyte 1 gives you different types of fragments compared with the analyte 2. So if you break down this, you get fragments with different masses compared with the analyte 2, which probably will give you it's totally different types of masses. And just an example, maybe we could think that one of the fragments we get from this, okay, this isn't working, but we get the fragment characteristic fragment coming from that analyte 1 could be 123.45. And then in case of analyte 2, a characteristic fragment could be like, let's say, 101.55. And now if we fragment those molecular ions and then analyze in the next step, next mass spectrometric step, we analyze the fragments. Then we can tell the difference. Because in case of analyte 1, we see this fragment, but we don't see this fragment. And in case of analyte 2, we just see this fragment, but we don't see this fragment. And now this is tandem mass spectrometry. So we analyze the fragments and we analyze the precursor ion or the mother ion. So this is called the precursor ion or a mother ion, and these are the fragment ions or daughter ions. And based on these differences, we can very selectively then analyze. We can tell that, okay, the analyte 1, we analyze the precursor and the fragments, and we notice that, okay, it has both these. Okay, then we know it's analyte 2. And if it has these, it's analyte 2. And that's the tandem mass spectrometric analysis and why it's very nice and selective. Because you can tell the difference even if the molecular weight of the original molecular ion is the same. And if the fragments are different, then you can make the difference. You can distinguish in between these two analytes in this case. Okay, so the fragmentation often takes place in between separate analyzers and like two quadrupoles. First quadrupole and then other quadrupole after the fragmentation step. And the fragmentation techniques used there are different types of them, but by far the most common is this collision induced dissociation, where we fragment these precursor ions with inert gas. Typically, it's either nitrogen or argon. But then we have some special cases when we also utilize these different other types of fragmentation. Okay, just a few words about the sample introduction. It can be In case of the volatile components, it's typically made by gas chromatography. The samples themselves can be volatile or they can be derivatized so that they are made volatile. For example, in case of fatty acid methyl esters, they can be analyzed by GCMS, of course. And when you want to make sure you have the correct identifications for your chromatographic peaks, it's very good to have GCMS. And afterwards, of course, then when you already know what the peaks are, then you might use some other detector for the quantitative work. Of course, you can also quantify with the mass spectrometric detection, but you can quantify it just a FID, flame ionization detector also. But it might be good step to include this kind of mass spectrometric detection to be really verify the identities of the chromatographic peaks. And yes, for the non-volatile components, the sample introduction is oftentimes made with LC, and these atmospheric pressure ionization techniques are often used. And phenolic components, I would say that by far the most common way to analyze these secondary metabolites, the phenolic components, would be these liquid chromatography, electrospray ionization mass spectrometry, or sometimes the tandem mass spectrometry, which is the MS, if you want to know more about the fragments and fragmentation in there. Okay, I will proceed into these examples of this ionization and also analyzers. But I think it might be good to have a 5-minute break at this point. You can digest and think about these issues and also write any comments you might have. So it would be good to have some discussion based on your questions and comments. So let's have a 5-minute break. I will pause the recording just for a short while. Okay, let's continue. No comments or questions still in chat box, but you can do that later. So electrospray ionization first is my example here. So it's an atmospheric pressure ionization technique, and the inventor of this modern version of ESI actually won a Nobel Prize a bit more than 20 years ago. And the ESI produces quasimolecular ions even for large molecules. You can analyze very large molecules, but you can also analyze small molecules. And what is a quasimolecular ion? And maybe it needs a bit of a clarification. So the quasimolecular ion is ion, which is quite often we just talk about molecular ions, to be honest. But if we would use the right terminology, we should call this, for example, is M plus H plus. It's the protonated molecule. So because it has its molecular weight is more than for the molecule because of the added proton, it's called a quasimolecular ion. But quite often I might just call it molecular ion, but it's quasimolecular ion, and this is a positive ion if we are having the ionization in so-called positive ionization mode. But if we are performing the ionization in negative ionization mode, we quite well could get these deprotonated quasimolecular ions, M minus H minus ion. Okay, so yes, that's the quasimolecular ion. Something has been added or something lost, but basically it's still quite close to the original molecule, so it's not a fragment ion. Yes, so What's happening in this kind of ionization is that we produced charged droplets. And there's a high electric field at the tip of this kind of capillary. And we have the liquid flow from the liquid chromatograph coming in. And this high electric field at the tip of this capillary causes charge on the liquid surface. And this charge is important there. As the ionization starts due to this happening. And what is also important in addition to this charged liquid is that we need to have these droplets that are charged. So, and the gas is used to nebulize or make those droplets and also to evaporate the liquid. So this is a process of droplet formation and evaporation in high voltage. So when the these droplets are formed, they are charged, and then the solvent will be evaporated slowly, and the droplets will become smaller and smaller. So they shrink in these kind of several fissions. And when they are very small, they are finally actually there are only single ions left. So all the solvent has been evaporated. So means that whatever the exact mechanism is, that we are left with single ions in gas phase at the end of the process, and we have got rid of all the liquid solvent. It's just that the droplets are used as a tool of the ionization in this technique. And why electrospray ionization? It's gentle. It doesn't cause that much of fragmentation by itself. So we can save the fragmentation to the separate fragmentation step, as I described with this tandem mass spectrometry. But this ionization itself doesn't cause a lot of fragmentation. There are examples of ionization techniques that themselves make fragments. And actually, the other example is electron ionization, which is just like that, actually. But ESI is very gentle, so gentle that we can sometimes also observe non-covalent associations. So even they might stay together in the process of this ionization. Often we also see multiply charged ions. One reason, an important reason for this is that electrospray ionization doesn't break larger molecules. They can stay as they are. And so the larger molecules we have, the more probability there is that we also have these multiply charged ions. This is only twofold, but some of them have 3, 4, or 5 charges and so on. And they can also be observed. As I mentioned, the quasimolecular ions are there. So almost the molecules, but something has been added or taken away. And my examples were this protonated or deprotonated. There should be in minus here, N minus H minus. But also additionally, we see these kind of adduct ions, sodiated molecular ions and the molecular ions with added potassium. And why do we see these? It's actually that in glassware, in laboratory ware, in all the stuff there's naturally present sodium and sometimes potassium, and they just end up reacting with the molecules. And quite often in the mass spectra, we also can see these type of quasimolecular ions or adduct ions actually when these kind of sodium or potassium are added there. Okay, you can find a lot of more in detail information of this ionization process in here. And we, as with all most of the ionization techniques, depending on the analyte, we end up choosing either positive ionization or negative ionization, meaning that we end up getting either positively or negatively charged ions. And uh, which one we choose is depending on our analytes. Some of the analytes prefer forming positive ions, and some of them prefer forming negative ions, and that's also affects our selection of the ionization uh, 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 voltage there, and the potential differences in either positive or negative. Okay, it's when we are analyzing utilizing mass spectrometry, and for example, this electrospray ionization, it's quite sensitive to some buffers. Volatile buffers are okay for routine use, but for this non-volatile buffers such as phosphate buffer, it's not possible. So if you are using phosphate buffers in some liquid chromatographic work, they cannot be used if the mass spectrometer is the detector actually. Eluent or the mobile phase pH, of course, affect also the ionization process, and we also need to remember that there's so-called matrix effect can be present. So when the sample contains high concentration of some salts or other components that are not our analytes themselves, that they can ionize in these conditions also are may compete of the ionization with the analytes of interest. And this kind of matrix effect is called ion suppression. So the conditions must be developed to remove or hide this effect. And actually one thing is of course to purify and or use the chromatography as sample introduction where there is not that much of extra stuff present in the ion source when the ionization is taking place there. Well, this was the electrospray ionization. Actually, I now jump to my other slide here. Then we have electron ionization as another example. And here in electron, remember now the difference. It's ESI or electrospray ionization, and this is EI or electron ionization, and this is just very different. And this is we bombard the sample with the electrons, and this ionization takes place in very low pressure. So electron beam is there sent from the cathode towards the anode, and that's where also the electrons bombard our samples. And there's this kind of hot filament used to produce the energy needed for the electrons, and it's typically the energy level E there is 70 electron volts. Oh, and the vaporized sample, typically from, for example, gas chromatography, are interact with the electron beam, and then various product ions are formed. Of course, we have the molecule itself can be ionized, but what is characteristic for electron ionization is that by nature, the ionization step itself causes a lot of fragmentation. So there's no separate fragmentation step like we in our example of this tandem mass spectrometry, where we have these molecular ions that are later on fragmented to the small fragments. But in electron ionization, typically or already in the ionization, you get all types of fragments. And sometimes even so much that you don't see much of the original precursor ion anymore. But this is in some cases this is quite useful that we have this kind of fragmentation. And this reason is that when we use this energy level of 70 electron volts, we will end up having very certain how would I say, each type of compound has its unique type of fragment profile, unique type of mass spectrum with its fragments. Let's say here, for example, we have this 2-ethylhexanal, its mass spectrum. So probably the original molecule here, a molecular ion here would be maybe this 128. I'm not sure, maybe. But what you see are mostly the fragments in this mass spectrum. Lots of fragments. But the fragment profile for 2-ethylhexanal is, it always needs to look like this. Remember, it doesn't change actually. When we are having this certain energy level in the electron bombardment, we always end up getting this mass spectrum that where the relative proportion of these fragments are like this. And why this is good is that you can compare your results to this kind of spectral libraries where there are thousands of mass spectra for different compounds, and you try to find your match, your sample mass spectrum and fragment profile there might have a match with the library database spectrum. And then if there is a match, then you can, based on that, you can more or less trust your identification. You can say, okay, this is the match. It seems that the 2-ethylhexanol that is found in the library database, it looks exactly like my own results. So probably my compound also is 2-ethylhexanol. Yes, so this is typical for electron ionization. Okay, just now just I want to show these different fragment profiles of different types of compounds that when the electron ionization or EI has been used. And now, of course, there are still one picture here to illustrate how some molecule where the molecular structure or the elementary composition is the same, but there's a bit of a difference. One of this is a ring structure, one is not. This is not. So really, this molecular ion here is, you see more of it if you are having the molecule in a ring as a ring structure here. If it's an open structure, typically it's even more easily just fragmented and you don't see much of the original molecular ion anymore there. Okay, so this is just the electron ionization. Okay, then the analyzer examples. I have a quadrupole, which is the low resolution analyzer, and time of flight analyzer is high resolution analyzer. And this quadrupole is actually, as you see, there are 4 poles, as the name says. Quadru, which is a 4 and pole structures. One pair is in positive potential, one is in negative. And what we apply here is radio frequency and direct current. And actually what is done here is that by adjusting this radio frequency and direct current settings, in certain time point, we only pass through one type of ion. So the settings are made so that, of course, we as users, we don't need to know about the radio frequency or direct current amplitude values at all. We just tell the instrument, hey, I want to monitor this ion 234.9. And so that in our computer and software sets these values show that only this ion can pass through to be detected. And this is the way how the analysis takes place. We always know, or the instrument, the software knows what the settings are. And if it's a certain ion fitting the settings and being exactly of this certain mass value, M to Z ratio, if it's present, it's let fly through with those settings that are unique to this. If it's not there, you don't see any signal. So this is monitoring these individual ions. And but what we often do is that we want you remember the scan mode. We want to scan everything, for example, from the mass 100 and to 1000. So it means we need to switch the settings all the time. Let's say within 1 second, we can very easily scan the whole mass range from 100 to 1000. It's just so that the radio frequency direct current amplitudes, they need to be very quickly changed. But only at one certain time point, always only one ion type passes through to the detector. But within 1 second, we can scan through the whole mass range of, let's say, 100 to 1000. The resolution depends on the direct current value in relation to the radio frequency value. And the quadruples are operated at constant resolution, which means that the radio frequency direct current ratio is maintained constant. So the ratio is constant, but the amplitude of both is going to be changed when we are want to pass through different ions of different MC ratios. So physically talking, for a given amplitude of these voltages, only the ions of a given MC ratio will resonate, have a stable trajectory to pass the quadrupole and be detected, and other ions with that specific time point will be destabilized and hit the rods. Okay. But when we are scanning, we are changing it all the time. Here you can read more about the scan and sim, which is what I already explained quite in the beginning. And quadrupoles are very sensitive when we are doing this SIM or single ion monitoring. We are just monitoring selected ions. But when we are scanning the whole ranges, then we lose a lot of the sensitivity, and then our quadrupole is not that sensitive technique anymore, actually. Now, the other example of the analyzer is the time of flight analyzer, which is high resolution. And what's happening there is, of course, now the size of the molecule, its mass, and also the charge state affects how fast they move in this kind of electric field. And there's this kind of time of flight tube where this flying takes place as a function of time. So what it says here is ions formed in an ion source are extracted and accelerated to a high velocity by electric field into this analyzer. The ions pass along the tube until they reach the detector. The velocity that is reached by an ion is inversely proportional to its mass, strictly or inversely proportional to the square root of its mz value. So it means that the higher velocity, the smaller the masses are there, actually, or the lower the mz values are. And this is important. The distance from the ion origin to the detector is fixed, so the time taken for the ion to travel there inside this analyzer is inversely proportional to its velocity. Of course, if it takes a long time for the ion to be detected, it's slow. Each MC value has its characteristic time of flight from the source to the detector, and this is the basis of this analysis there, and also the resolution of this analyzer. Now the tube itself, it's described here. It's linear, but actually we don't use it in a linear mode in a sense that what we usually do that is that we start to accelerate the ions here, and they come to this kind of electronic mirror called the reflectron. And after the reflectron, the ions are mirrored back, and they are able to fly again the same path or same before they reach this detector here. Actually, this is not only to give more time to fly. It's the increase the resolution that is caused. This increase is also the reason is that the dispersion of the ions of the same MC value is minimized when this reflectron is used. And this leads to a great improvement of resolution. And actually, what is happening, why the dispersion is minimized, is that this reflectron takes away the differences in kinetic energy of the ions of the same MC value. And the resolution will be better because of that. Okay, so high resolution, high accuracy analyzers, and also if not as sensitive as quadrupole when you are monitoring just the selected ions, it's then in the scan mode, if you are scanning a large range of ions, the sensitivity does not suffer because of that. In time of flight instrument, it's a fast scanning instrument. Okay, so actually what I want to show you now is first of all, I was talking about the tandem mass spectrometry with instrument where we might have two quadrupoles. And now my first animation is an instrument where we have these two quadrupoles, and in between we have the fragmentation step. So this is about the tandem mass spectrometry in this example. I will have a YouTube animation to show that for you.
Your samples are precious, and turnaround time is critical to the success of your organization. A sensitive yet rugged instrument that provides day-in, day-out performance is cornerstone to your workflow. Now, productivity is elevated to a new level with the Agilent 6495C triple quadrupole LC-MS, combining extreme sensitivity with robustness, reliability, and accuracy. Based on proven iFunnel technology, the Agilent 6495C triple quadrupole LC-MS includes rugged ion optics, collision cell, and detector. All these elements work in concert to bring users more confidence in their results. Outstanding quantitation begins with the Agilent Jetstream ionization technology. Agilent Jetstream technology provides efficient desolvation or ionization of a broad range of compound classes. A hexabore ion injector capillary increases the amount of ions entering, achieving a significant increase in ion sampling for a tenfold gain in signal intensity. With VacShield, the ion injector capillary can be easily removed without venting for increased uptime. The first ion funnel operates at high pressure, collects ions, and propels them forward. The second stage funnel operates at a lower pressure, tightly collimating the ion beam for further sample enrichment. An optimized octopole ion guide provides high-efficiency ion transmission over a wide mass range. Newly engineered ion transfer optics increases precursor ion transmission for a higher sensitivity and precision.
Okay,
the optical lens elements reduce contamination and enhance the ease of ions, improving overall system robustness. Hyperbolic quadrupoles emulate the shape of a hyperbolic quadrupole field for enhanced transmission efficiency in both quads.
We are filtering
the first quadrupole mass filter only allows ions of the target analyte to pass through to the collision cell. The curved and tapered hexapole collision cell design maximizes ion transmission while minimizing detector noise from neutrons. An axial cell acceleration voltage ensures fast and sensitive MSMS without crosstalk effects, even at the fastest MRM dwell times. The second quadrupole serves as a mass filter for fragment ions produced in the collision cell. For quantitative analysis of a target compound, the second mass filter is operated in a selective ion monitoring mode for target fragment ions. Finally, the advanced detector assembly features a high-voltage conversion diode that enables highly efficient positive and negative ion detection. This design improves signal conversion efficiency while maintaining very low noise.
Multiplier.
The high-performance 6495C triple quadrupole LCMS not only continues the innovation of triple quadrupole technology, but also elevates the sensitivity and reliability to a new dimension, facilitating the detection at low attogram levels with excellent precision.
Yes. Hybrid. I was also talking about the hybrid mass spectrometers, and they are such that we are combining two different types of analyzers. And very typical example nowadays is the QTOF, where we can use the quadrupole to filter ions to be analyzed in very high resolution in time-of-flight analyzer. So a quadrupole can be used there first to select different ions to be fragmented, which are then analyzed by the high-resolution time-of-flight analyzer. So these are hybrid MSMS instrument. We can use what we do there and can do is the MSMS tandem aspect. Just that the first analyzer is quadrupole and second one is the time-of-flight. So here you see, and actually my other animation is also from Agile, but it's has to do with this kind of QTOF instrument. I will show that animation, but now nice, we have some comment in chat box. Let's see. Exam. I have a home assignment from you. I have not described it yet. I will show the home assignment at the end of this lecture. So if you mean that we don't have exam, but it's a home exercise or home assignment that you need to do by the end of April. But let's come to that later. Okay, QTOF. And now let's see the animation. It's quite similar type of animation actually, but now the second analyzer there is not a quadrupole, but it's the time-of-flight analyzer.
Whether you are identifying proteins and characterizing post-translational modifications, searching for metabolite biomarkers, or finding impurities in pharmaceuticals or food, the Agilent 6510 quadrupole time-of-flight LCMS is an outstanding choice. It delivers better than 2 ppm mass accuracy for MS and better than 5 ppm mass accuracy for MSMS. It also delivers wide in-spectrum dynamic range and unsurpassed QTOF sensitivity, all in a reliable and easy-to-use system. Great sensitivity starts with superior ionization technology. Agilent's patented nebulization technology produces finer droplets and delivers more ions to the mass spectrometer. A second nebulizer introduces reference mass solution that ensures continual mass axis correction for the best possible mass accuracy. High-volume counterflow drying gas reduces noise related to incomplete drying of solvent droplets and keeps the sampling capillary and ion optics cleaner for reduced maintenance.
Okay, so we guide the ions
A
forward.
thin skimmer aperture, carefully matched hole size, and short capillary to skimmer distance reduce beam broadening. An on-axis octopole ion guide provides nearly 100% ion transmission over a wider mass range. Patented lenses enhance high-mass ion transmission and increase sensitivity over a wider mass range. The quadruple mass filter allows only ions of the target mass to pass through.
We
The
now
hyperbolic
select
shape of the
only
rods
these green ones, so
enhances
we
ion
pass through
transmission
only
and spectral
selected
resolution.
MC ratios here.
In the hexapole collision cell,
This is the collision
precursor
cell.
ions strike collision gas molecules, generating product ions and neutral fragments. Linear axial acceleration and high collision gas pressure ensure that all ions exit the collision cell with nearly identical energy. This allows the same mass calibration factors to be applied to MS and MS-MS ions. The result is better than 5 ppm mass accuracy for MS-MS ions.
Then this daughter of
Another
fragment ions
octopole
are
ion guide keeps
analyzed.
the ions together while allowing
they
excess collision
are
gas
going
to be
to be
pumped
analyzed in
away.
the
A
time of
quadruple
flight
ion guide
analysis.
flattens the stream of ions for better transmission through the slicer. The slicer reduces variations in the vertical momentum of the ions. Ions with too much vertical momentum do not reach the pulsar. This improves mass accuracy for all ions.
So here is how the ion separation takes place.
The flight tube is constructed of special materials with very low coefficients of thermal expansion, so it is less sensitive to temperature changes. The reflecton compensates for minor velocity differences, improving the resolving power of the 6510. The microchannel plate detector converts the ion signal from electrons to photons and back to electrons. This electrically isolates the high voltage flight tube and front of the detector from the signal passed to the electronics. ADC digitizer electronics provide extremely high mass accuracy over a broader dynamic range. The 6510 offers outstanding in-spectrum dynamic range for a time-of-flight instrument. When you need the ultimate in LC, MS, MS power and versatility.
Okay. And last part here, I just this is the detector part. Let's remember so that like a chromatography point of view, we can consider whole mass spectrometer as a detector. But this is not just technically speaking the detector part, which is the last part here, which is most typically it's the electron multiplier, as you've seen in this animation. Sometimes it's also can be photo multiplier in some of the instruments to really they get the see the signal. In the time of flight instruments, as you saw in the animation, that microchannel plates or multi-channel plates are used. They have a high sensitivity and good time response, and they are large. They have a large area, and in this kind of planar structure in there, and they are perfect for the large acceptance volume of the needed for these type of mass specs. So it's possible to detect many ions at the same time, and this is very important for this this kind of analysis used in the time of flight. Okay, was the mass spectrometer. Can really remember also this we have a huge selection of techniques, but the electrospray ionization and the quadrupoles, time of flights, they are the very typical ones. Also, in the analysis of phenolic compounds like flavonoids and other phenolic acids, and and I have a task for you or assignment for you, and this is actually what part of my evaluation of the course. So your task is this, and you should be doing this by the end of April. Let's write it here. Deadline. So I want you to write something about describe two different ionization techniques applicable to mass spectrometry and two types of analyzers. So ionization techniques and analyzers. These must be different from those discussed in the lecture notes. Also give examples of what they could be used for. And actually, I think what we do is that in from my point of view, I want you to find especially find these kind of examples in food sciences. In the same file, also attach example pictures of each of these techniques. So two ionization techniques, two analyzer types. As such, or as part of the big instrument consisting of other parts as well. So there are plenty of pictures online. Choose the ones that are as illustrative as possible. And deadline will be 30th of April, and I think it could be something like 2-3 pages with line spacing 1.5 font size. It can be, let's say, depending on what you choose, font size 11 to 12. Roughly, I'm not that strict in the how is it 2 or 3 or even 4 pages. It may think that you will describe this and also give some examples. So I will also, when I'm sending you this presentation and recording, I also can have this instruction sent to you. Has Professor Atmasol sent you already this link to this FUNET file center where you can download the recordings? Have some of you already downloaded them? Please comment me or tell. Have you got those download links already from the 2 previous lectures?